I'm Moungi Bawendi, and I run the Bawendi Lab in chemistry here at MIT. And we work on quantum dots, all aspects of quantum dots, from their basic properties to the chemistry, characterization, and all sorts of applications, ranging from biology to displays to solar energy, and probably others that we haven't yet discovered. I started working on this when I was a postdoc at Bell Labs with Louis Bruce, who discovered what's called the quantum size effect in these very small particles of semiconductors that are a few nanometers in diameter. And at the time, it was really curiosity-driven. It was a property of looking at the evolution of the quantum effects from molecules to the bulk material. And I started working on this as soon as I got to MIT, really driven by the need to, or the curiosity to understand that physics. And that curiosity drove us to make better and better samples because we needed them to tease the physics out. And so we spent probably the first 5 years at MIT developing better and better methods of making particles, making these very small particles. More narrower size distributions, better crystallinity, and then we ended up developing what we call core shell particles. We have one kind of particle in the center surrounded by a shell of a different kind of material to protect the inner particle. And what we found was that these core shell particles ended up having great properties that they could absorb light and re-emit light of a different color with very high efficiency. And it's around that time that we realized, and us and many others in the community realized that, well, maybe these things could be useful for something because they're very colorful. The colors are really saturated, and they're like little pieces of rock. So they were the equivalent of organic fluorophores, but with narrower, more saturated colors, and probably with more stability. And that's when we started thinking about applications in emissive colors. The two applications that we're still working on today came about right around the same time. The biology of using these small particles to tag cells or to tag parts of cells, maybe for in vivo applications in animal research, because they were very small and we could change the surface to target different molecular biological objects. And around the same time, we also started working on trying to get light emission in what's called electroluminescence by injecting charges into the particles like you have in an OLED display, like in your Samsung phone, for example. And OLEDs were just starting out at the time. And we thought we might have something that could be just as good as OLEDs because these things were going to maybe be more robust than OLEDs. And so we started working on that at the same time. The biology application went a little faster in terms of commercialization. In the late 90s, we helped co-found a company, Quantum Dot Corporation, to provide particles to biologists. The display took a while longer, and the electroluminescence that we had started working on, that's going to take a lot longer. But we found another way to make these things to use these things for displays, which is what we call downshifting. These particles are really good at absorbing blue light and re-emitting any color you'd like in a very saturated way. And so these are now used in a number of LCD televisions where the blue light is being created by blue LEDs. And then quantum dots then take that blue LED and make the green and the red lights that then power the colors of your screen. And with that, you get very saturated colors. The blacks look blacker. The reds and the greens are really kind of amazing to look at. And the efficiency, the energy efficiency of the TV can also go up as a result. And there are a number of models now on the market. Sony sold a few models a few years ago based on technology that was developed by an MIT startup, QD Vision. Samsung's high-end TVs this year have quantum dots in them developed within Samsung. So it's really taken off now, and just in the last couple of years, the display part.